Welcome to qnawire.
Hi, so we're here where I want to know how we were able to find the decomposition of this wave function as a product of three different, as a linear combination of these three different eigenstates. So in order to do this, what you need to remember is that the eigenstates come from the eigenvalue equation, that is the Hamiltonian times the wave function is going to be equal to the energy times the wave function. So essentially what we need to do is from the representation of the matrix of the Hamiltonian, we're going to find the eigenvalues and eigenvectors. In this case, since the Hamiltonian is not provided to us, the only thing that we can know is that each of these eigenvectors are going to correspond to the eigenvalues according to that. So, for example, the vector 1 over 2 minus 1 square root of 2 minus 1, when we apply it to our Hamiltonian, is going to be equal to minus 1 times the same vector. 1/2 of the minus 1 square root of 2, oops, minus 1 vector. Similarly, with the other two states, we're going to have that the Hamiltonian applied to 1 over square root of 2 of minus 1, 0, 1, is going to give us 0 directly. This is going to be our 0 eigenvalue. And lastly, the last eigenvector that is provided to us is the 1/2, 1 square root of 2, 1 vector, that upon action through the Hamiltonian is going to give us 1 times the 1/2, 1 over square root of 2, 1 vector. So in general, whenever we have this equation, we can find the eigenvalues and eigenvectors as the determinant of the metric representation of the Hamiltonian minus lambda times the identity. This is going to be equal to 0. This is going to give you solutions for lambdas, in this case lambda 1, lambda 2, and lambda 3, which are the values that are given to you. And upon substitution on your secular equation on the determinant, what you're going to get is the corresponding eigenvectors. So this way is just a representation of a wave function in terms of eigenvectors of an operator. In this case, I employ the Hamiltonian just as an example. It could be any other operator that you're dealing with.